So cyclohexane. So cyclohexane, I'll do that one here. Here's cyclohexane. It's just, well, let's just do it here. See, it's hard to draw so it's got 6 carbons, as the name implies, hexane, and each one of them's got. Now, normally these carbon-carbon bonds would be free to rotate. But as soon as you wrap it around on itself, you run into a problem. It's not exactly free to rotate. So what's interesting about this, you can get 2 conformers of butane, or cyclohexane, and I'll try and switch this so that you can see this. I have to back up, zoom out. Okay, so looking down on this, here's my 6 carbon atoms. And these are all, this model is arranged so, of course, all the bonds are at the corners of a tetrahedron, 109 degrees between them. And you notice something interesting about that when you have this model. These hydrogens stick straight up. And these hydrogens down below here are sticking straight down. We call those the axial hydrogens. Why? Because there's a rotation symmetry right here, right? 3-fold symmetry right there. And they're all pointed along the rotation axis. And these out here, those are called the peripheral hydrogens. What your text uses, oh, they call it equatorial hydrogens in your text. So they're pointed out to the side. Now, the most interesting thing about this arrangement, though, is if I look down here, this axis, it's kind of sloppy, but I think you can see that it's not a planar molecule, right? This carbon droops down, and this one sticks up. And that's the so-called chair. You can imagine, you know, if this had a canvas over it, you could sit down, and your head would be up here, and your feet would be down here. So that's the chair form. Now, I could have arranged this like this. And with the canvas on it, it now becomes a boat, right? So that's the boat form. And you can see it's completely different, right? Now I have 2 axial hydrogens sticking up like this. You'll notice it's 2-fold symmetry, right? Not 3-fold rotation. And so it's completely different. And so these 2 conformers, now I can switch from one to the other. It's actually pretty easy, well, on this model anyways. If I sort of twist this, see, like, oh, see it happen? It involves rotation. You know, I have to bend bonds to do that. So in fact, not only is it higher energy to do it in the boat form, it's hard to convert between them. Interesting, there's another transformation that can take place that's actually more common amongst these, is that, you know, this is the one sitting down, and this is the one sticking up in the chair form, but I can do another twist like that, and the one that was on the corners, or one of the ones that was on the corners is now sticking down, the other one's, so you see what happened, it rotated where the head of the chair was. And that required rotation of 3 bonds simultaneously. So it's not very common, but if you have a mole of them, it happens. So it turns out the activation energy for that is around 42 kilojoules per mole. So even though it's the same molecule, you know, in other words, it's the same molecule now, in order to make this one now the foot and this one the head, I had to, you know, really twist this thing, and it ends up at the same energy, but the barrier between it was 42 kilocalories per mole. So it actually these conformations sit there. If you made it once, it sits there at room temperature.